Around the world, at any given moment, 2,000 thunderstorms are churning through the sky, producing up to 100 flashes of lightning every second. Lightning might seem like something we've got all figured out, but in fact, the details of the physics behind those flashes is still a bit of a mystery. Los Alamos National Laboratory studies lightning because it produces signals similar to those from a nuclear explosion. That understanding is helping us develop better instruments for nuclear test-ban treaty monitoring and, in the process, allowing us to answer a lot of questions about lightning itself. Research shows that enhanced lightning rates can indicate severe weather. Maybe someday our understanding of lightning will allow us to use space-based lightning detection to predict tornadoes and other severe weather events with enough lead time to prevent casualties.
Convective storms hold an extraordinary surprise. Under just the right conditions, they fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs.
Ordinary lightning happens when electric fields build up inside thunderclouds. Electrons rush from one part of the cloud to another to try to cancel out the growing voltage. The flash of light we see traces the path of the charged particles, which heat the air 5 times hotter than the sun. Under the right conditions, electric fields in a thunderstorm can create a powerful avalanche of electrons, shooting upwards nearly as fast as light. The electrons collide with air molecules, in turn producing gamma rays. Earth-orbiting spacecraft have been observing gamma-ray flashes from thunderstorms since at least the mid-1990s. Next, the gamma-ray energy transforms into a pair of particles, an electron and a positron. Successive collisions between these particles and other air molecules create a new batch of positrons and electrons, and the cycle repeats. A continuous feedback loop forms, like nuclear fission. It's a natural, self-generated, self-sustained particle accelerator, says Dwyer. Once the feedback loop gets started, he says, it can discharge parts of a thundercloud as fast as lightning. And, because the cascading electrons and positrons generate more gamma rays than visible light, the whole process is practically invisible to the human eye. Researchers once thought that gamma-ray flashes from thunderstorms were a weird byproduct of ordinary lightning. Now they are thinking it is a sign of dark lightning instead.
Narrow bipolar events, NBEs, are a recently discovered distinct class of intracloud lightning discharges whose associated processes produce the most powerful very high frequency, VHF, radiation observed from lightning but are optically weak. NBEs are thus the prime candidate for proposed satellite-based VHF global lightning mapping and storm tracking missions. Strong correlations between total lightning rate and convective strength, especially in terms of the height of 30 dBz radar echo, are found. However, much weaker correlations between NBE rate and non-NBE lightning rate and between NBE rate and radar-inferred convective strength are found. Though NBEs occur in the same storms as other lightning, they cluster more closely in both space and time and may be indicative of specific types of storms and/or specific stages in convective development. Indeed, NBEs are more prevalent in, and perhaps indicative of, the strongest convection. However, even the strongest convection, as inferred by radar, does not always produce NBEs. Gamma-ray flashes are not detected by optical instruments.